I think we ended with oxidation, right? Primary, secondary, tertiary alcohol oxidation. And we also covered yesterday the dehydration. Right, Holby? Yes?
I'm sorry. Say right, Holby.
I said correct. We covered dehydration yesterday. Yes. Okay, thank you. All right, so we covered primary and secondary and tertiary alcohols. Dehydration is an elimination. Dehydration, we're taking water out of a molecule. And so when you do a dehydration reaction, you can have the final product plus water. Water is a product of this dehydration reaction. You actually do get a molecule of water. Yeah, we covered this one, right? This molecule here, here is the minor product. We've got an OH here, and there's an H next to it here. There's an H next to it here. If we eliminated the water there, we get that double bond, and it's the minor product. If we take this hydrogen and this OH, we get rid of a water molecule, and we get a double bond where we remove the water. Why is this the major product? Because it has more carbons attached to the two carbons with the double bond. That's why that's the major product. And that's Zaitsev's rule. Zaitsev's rule says you're going to get the most substituted alkene. Most substituted. This has 3 substituents on it.
Bless you.
These are not substituents. Those are just hydrogens. This one only has 1 substituent on it. So that's the major product. Here's another one. We won't dwell on it, but there's this is 2-methyl cyclohexanol. You got cyclohexanol. You got a methyl group over there. Yeah, and because we got the methyl group over there, this double bond is going to have 1, 2, 3 carbons on it. You're going to have 3 carbons on that double bond. If we could, there's a hydrogen over here, so we could remove a water molecule here and get this molecule. We could get this molecule. Now, where's that methyl? The methyl's right here. But this double bond has only 1, 2 carbons on it. Ends up with only 2 substituents on it. So it's the minor product. This one ends up with 3 substituents on it, and it's the major product. There is a hydrogen here. It's not written because that's a line diagram. There are 2 hydrogens over here. Not written because we got the line diagram right there. But there is a hydrogen that can go off with this OH and form that double bond. But that would be minor. That would be your major product. You can come back and look at these. Okay, there is another way of dehydrating alcohols, and it will form ethers. So there's 2 ways of dehydrating an alcohol. Intramolecularly, what do I mean by that? You take the water molecule out of one molecule. That's what we just studied. So you can take a this is what we just learned, the dehydration of an alkene, of an alcohol. You remove that water, and what do you get? You get an alkene. Now we're going to look here at removing a water molecule from between 2 alcohol molecules. Let's look at the simplest case of that. Let's take methanol. This is also dehydration. Oh. There's two methanol molecules. But you can see there's water right there. We're getting the OH from one molecule, we're getting the H from another molecule. This is the dehydration intermolecularly, from between two molecules. And if I took that water out there, hopefully you can see this. There's our oxygen. It's going to now be attached to the carbon of the other alcohol. Plus, we remove the water molecule. There it is. That water. That's where that water came from. And this is not an alkene, obviously. It's not an alkene. It's an ether. What is an ether? Any molecule that has that functional group in it. Carbon, oxygen, carbon bond is an ether. Dentists used to, I think they still do, use some kinds of ethers. Actually, a lot of different kinds of ethers are anesthetics. We'll see a couple examples here in a minute. Different ethers that are anesthetics. This is an ether. And now you could not get, you can't dehydrate methanol and form an alkene. An alkene requires two carbons. All right, so there's no way to, you can't just kind of take that water molecule out of there and end up with a double bond there. A carbon-carbon double bond. There's only one carbon. Okay? So this one can't dehydrate the way we've been doing it. So this is a good example to show ethers. But even if you could make an alkene out of it, you can make an ether out of it if you run the reaction properly. What they're saying right here, at low temperatures, you could produce an ether at higher, not with methanol, but with an alcohol that has 2, 3, 4 carbons in it. You could either make an ether out of it, or you can make an alkene out of it. Let's take an example. Let's just take a little bit bigger alcohol, ethanol. These are all hydrogens. So you could dehydrate ethanol intermolecularly between two molecules of ethanol. You can remove a water molecule, and you're going to get this carbon-oxygen-carbon bond. All right, and you'd get that ether. It's a different ether. So just keep in mind what we got here. We got a carbon-oxygen-carbon bond. That's why we're calling it an ether. But this is a class of organic compounds. The first one was dimethyl ether. This one up here is dimethyl ether. So we're saying on either side of this carbon-oxygen-carbon bond, if we got an ether, got a carbon-oxygen-carbon bond, what's on either side of it? Methyls are on either side of that oxygen. All right, let's show you how smart you are. What would you call this one? diethyl ether. Then there's an ethyl on each side of that. And there's only two of them. Diethyl ether. Diethyl ether. So these simple little ethers, that's the best way to, I mean, this is an ethyl group. Right? It's an ethyl group. You could have methyl ethyl ether. Dipropyl ether. Ethyl propyl. Ethyl isopropyl ether. Okay? Any of those substituents that you know about. Put one on one side and the other one on the other side, and you got a different ether.
You can't have a methyl ether, though. You have to have two.
Yeah, you can't have just a methyl ether. It would be a dimethyl ether. And if you use the name methyl ether and say, well, they're all methyls, well, you need to tell me that they're all methyls. I'd say, well, okay, there's something on either side of the oxygen. Do you mean they're both methyls? Or so you would say methyl ethyl or dimethyl. You won't have trimethyl. You can't put three things around the oxygen. You won't have the trimethyl ether. Yes?
So then the oxygen only has two bonds?
Yeah, the oxygen only has two bonds. Look at water. Oxygen only has two bonds. Okay? It's not like carbon. Okay, this goes back to 1305. There's carbon. Four valence electrons. Here's oxygen. 6 valence electrons. It only wants 2 more. Then it has 8. Doesn't get 4 bonds around it. Reaction map of alcohols. Wait, how many more slides are there here? Yeah, there are some more. I don't know why we're getting to the reactions. Well, we'll come back. We'll come back and summarize reactions here in a minute. Aromatic alcohol, phenol. Don't get phenol mixed up with phenol. Phenol is a benzene substituent on an organic compound. That's phenol. Remember, YL is a substituent. Methyl, ethyl, isopropyl, tertiary butyl, phenol. But this is phenol. This is actually a compound. It's a benzene ring with an OH group, and it's an aromatic alcohol. So what we are doing is building a little family of 6-membered rings. So by Monday, there'll be more next week. Yeah, and I would suggest a 3x5 card for each of these. And I don't know if I'm forgetting any right now. There's 5. Okay, think about those 5 for a second. I'm going to point to them, and just someone, if you are pretty confident, 2 or 3 of you at a time, say what their names are. You ready? Everybody ready? Thought about what those are? The names of all 5 of those? What's the name of that? Cyclohexane.
Cyclohexene.
Benzene. No cyclo. Benzene. Toluene. Phenol. So there's 5. Phenol. Yeah, but you would want to put your CH3 right at the end there, because see where is that line going? It's going to that carbon. Okay, it's not. The methyl isn't just sitting over there. That is a bond, and what is it bond to? It's bonded to the carbon. It's not bonded to any of the hydrogens.
Okay.
It's bonded to the carbon of the methyl group. Okay, hexachlorophene, an antiseptic. You don't have to memorize these structures. But here's your phenol, or carbolic acid. You can see things have other names. You don't need to worry about that name. Just that name, phenol. Hexachlorophene. Hexachlorophene. 1, 2, 3, 4, 5, 6 chloro groups on there. You can see right here, here's your phenol, phen, right here, and you got a methylene linkage between the two. That's hexachlorophene. Hexyl resorcinol, you might have heard the names of some of these things. Another antiseptic. This is a good one. This is a great little tongue twister. Okay, because, it puts a lot of things together. Notice that this is in the ortho position. Remember, we got phenol. That's our parent molecule right here. Ortho, meta, para positions. So what position is that in? It's in ortho. And what is it? It's a phenyl group. Ortho, phenyl, phenol. All right? You don't have to memorize that, but that distinguishes right away. There's the phenyl. There's the phenol. This is a substituent on that molecule. Orthophenylphenol. Another antiseptic. The only one you should memorize is the phenol. I'm not going to worry about reactions of phenols. Okay, ethers. Here's, I already introduced this. Ethers. The general formula is ROR, where R is any kind of a carbon species. It can be 1 carbon, 2 carbons, 5 carbons. And you got a carbon on either side of the oxygen. You don't have a carbon-oxygen double bond. These are single bonds. Carbon-oxygen single bonds. There is dimethyl ether. I'm not going to make a big, huge point out of this. We've already talked about the difference between an alkane and an alcohol. Non-polar. This is non-polar. On one end, this is polar. These molecules don't have any strong attraction to each other. Boiling point, approximately 0 degrees centigrade. Let's not get hung up in decimal points here. 0.5, that's a half a degree centigrade, around 0. This is approximately 100 degrees centigrade. 100 degrees higher. Why? Because our 1-propanol looks like this. And so another 1-propanol that looks like this can hydrogen bond to each other. They're sticky. This is like having honey on your fingers. My fingers are kind of stuck together. All right? They don't just come apart real easily. These molecules come apart real easily. They just, I don't care. I don't care whether I stay in the liquid or evaporate out into the air. You know, there's not a strong attraction between the molecules. There's a strong attraction here. So if this was your beaker full of this stuff and you're heating it up, you got to get enough energy in here to break these bonds for that molecule to finally evaporate and boil away. You need energy to break that attraction. All right, so that, and where does that energy come? It comes as you get to higher temperatures, you get more energy. So you got to get up 100 degrees higher. Now, that's not butanol. Why? Because they're trying to get molecules that weigh about the same amount, about the same molecular weight. They should have somewhat similar boiling points, and they don't. That's a big difference. Now, here's your ether. Approximately 10 degrees centigrade. So only mildly polar. And why isn't that as polar as an alcohol? Because there's no hydrogen on the oxygen. There's no hydrogen. When you put a hydrogen on here, now you have two atoms that have very different electronegativities. So you get a stronger negative, a stronger positive here. Ethers, oxygen has a higher electronegativity than carbon, but not as big a difference. Hydrogen is electronegativity at 2.1. Carbon, I think, is 2.5. And oxygen is 3.5. 3.5. So there's the bigger difference between these two in terms of electronegativities than these two. Still a difference. So a little bit higher boiling point, but not hugely. Okay? That's the point. We're going to see this slide, or similar slide here, as we get into chapter 13. Common names of ethers. Okay, so common names. When you see two substituents that you can, you got, here's your carbon-oxygen-carbon bond right here. This oxygen is not bonded to that hydrogen. I mean, that hydrogen's down here. So that's a carbon-oxygen-carbon bond. It's an ether. So name that ether. There's a kind of a hush all over the room. I'm not a singer. What are the two substituents? What is that? That's a methyl group. What is that? Isopropyl. So that's isopropyl, methyl, ether. Okay, does that make sense? Just look on either side of the oxygen and say, what do we got there? We got a methyl group there. We got an isopropyl group there. And I guess alphabetize them. But I don't think I would get too bothered if they weren't in alphabetical order, but you did have them named properly. Isopropyl methyl ether. So you should start identifying that as an isopropyl group. Bonded to the middle carbon. There's 3 carbons here. That's not a propyl. It's an isopropyl. Okay, what do we have here? What are the two? What is this? Ethyl. And what is this? It is benzene, but when benzene is a substituent, we call it what? Phenyl. Phenyl with a Y. L. Ethyl, phenyl, ether. That is not phenol. You got the oxygen there, but you don't have the hydrogen. Phenol is an aromatic alcohol. This is one of the substituents is a phenyl group. The other is an ethyl group. Ethyl, phenyl, ether. Yeah, it does say list them in alphabetical order. Oh, okay. All right, we have to learn this. How do we deal with it if it isn't a simple ether? There's a molecule right there. So what we have there, notice there's 5 carbons. And we have a but just keep in mind, we could have this, 5 carbons. Okay, when you start drifting away from just a simple 2 methyl groups, or a methyl and an ethyl, or a methyl and an isopropyl, you start getting here where you got a methyl on one side, but you got a pentyl group on the other side. And you say, well, why don't we just call this pentyl or methyl pentyl ether? Well, this would be methyl pentyl ether too, wouldn't it? There's a pentyl. But it's not attached at the end, it's attached here. Or it could be here, and it would still be methyl pentyl. All right, now it gets confusing. When you get big molecules, it starts getting confusing. Where is that? Where is the carbon-oxygen-carbon bond? And so what we do now in this case is we talk about this as a substituent. And it's not a methyl group, it's a methoxy. This is a methoxy group. So add that to your repertoire of substituents. That's a methoxy substituent. And now if we look at that as a substituent, what can we do? Well, we can say, what carbon is it on? What carbon is that on? It's carbon number 1. So this is, the longest chain is 5, pentane. It's got a methoxy substituent on carbon number 1. And this bottom one here would be 2-methoxy pentane. It's got a methoxy substituent, but it's on carbon number 2. 2-methoxy pentane. I probably won't throw real complicated molecules at you like this. You know, nothing more than to recognize, oh, that's a methoxy group. If that's a methoxy group, let's stick with our 5-carbon molecule right here, and you name this one. All right? Think about this. Remember, we're trying to be systematic. If that is a methoxy, that methyl with an oxygen, methoxy, what is this? Ethoxy. This is an ethoxy group. An ethyl with an oxygen. It's not an ethyl, it's an ethoxy.
So it's a methoxy liquid ethoxy. With the pentane.
Yeah, so give me the full name of this. 2-ethoxy pentane. Okay? I don't think we need to go further than methoxy and ethoxy. But part of this, like I said, you probably think I am trying to turn you into organic chemists. I'm not. But I am trying to turn you into a person that can listen to an organic chemist or a chemist or a pharmaceutical person or whatever and kind of stick with them. Oh, he just said he's got a ethoxy on there. It's a menthanol. You know, I can look at the name of this and I can see some of the functionalities are in there. You don't need to be an expert on it. You need to be able to relate and connect with the chemicals that you'll come into contact with as a nurse. You can't ignore this. Nursing has gotten more complicated. My wife studied to be a nurse. She's a bachelor's level nurse. She hasn't practiced nursing for a number of years here, but 15 20 years ago when she was becoming a nurse, it wasn't as complicated as it is today. The drugs have just exploded in terms of the pharmaceutical things that are there and interactions of things. Don't worry about, you burn them. You can burn ethers. They burn. Diethyl ether is highly flammable. And diethyl ether is a common solvent in an organic laboratory. You open a bottle of diethyl ether and you can smell it. You can kind of see the vapors coming out of it. But it is you don't want to be smoking around a can of diethyl ether. It will burn very quickly and explosively. Okay, this is just going over what I told you. Here's two alcohol molecules forming an ether. We've kind of gone through that. There's ethanol, and you're forming warm, not real hot. Real hot, you might form the alkene. Lower temperature, you'll form the ether. Okay, here are some anesthetics. Diethyl ether. This was what the dentists did use. They'd put it on a cloth, put it over your face, and you'd go to sleep. Wake up with fewer teeth, and pay a big bill and walk out. Diethyl ether. Penthrane. You can see that's an ether, but they've got 2 fluoros, 2 chloros, and a hydrogen on there. Penthrane. And there's a whole family of these, and they, depending upon their solubility in your bloodstream, depending upon how quickly their boiling points, because the lower boiling point will turn into a vapor as it comes back. They inject you with it, or however you're exposed to it. Your body then is bringing the blood through the lungs, and it's evaporating into the lungs, and you're exhaling it. And then its effect wears off. I talked with an anesthetist, a master's level nurse anesthetist, who told me, yeah, the doctor says I want this patient to be lucid in 30 minutes. 30 minutes after the operation. I'd like them to be able to move out of the recovery somewhere else. They figure out what will get out of the human system in 30 minutes. Or the doctor tells the anesthetist, this person is going to be in pain for 4 to 6 hours, a lot of pain. So we want an anesthetic that's going to be slow acting and stay in there a long time. So they use a different anesthetic. So boiling points, solubility in the bloodstream, different things affect what anesthetic they would use. And I don't think they're all ethers, but there is a lot of them that are ethers. Okay, all you need to learn here is what a thiol is. And a thiol is an organic compound that has an SH on it. It's not an alcohol, it's a thiol. Now notice right here, periodic table, oxygen, OH, alcohols, sulfur, SH, thiols. Okay? It's still just an SH group. It's an S with 1 hydrogen. 3-methyl-1-butane thiol. We won't even go into naming them. Just know, be able to recognize. I could see a multiple choice question. Which of the following functional groups is a thiol? You have an OH, an NH2, a chlorine, an SH. You need to identify what does a thiol mean. It's a sulfur on a carbon molecule. Cysteine is an amino acid that has an SH. Yeah, an SH group on it, cysteine. They stink. really bad, parts per billion levels of thiols, and you can detect them. Okay? This is what skunks produce. They produce thiols. Here's Pepe Le Pew. Okay? Pepe, oh, you must know French too. Pepe Le Pew. All right? So here's Pepe Le Pew heading off for his date with his roses. The roses are giving off these nice alcohols, very fragrant. Pepe doesn't even notice himself. But he is giving off thiols. Oh, then that is actually true. If you went into a lab that was using thiols, you'd go walking in the lab, you go, whew, take your breath away. But if you stayed there for a half hour, there might be people working in there. They say, what's wrong? Well, it stinks in here. What do you mean what's wrong? It's awful. I mean, it's like turning my stomach. Oh, we didn't notice. Okay? Because it wears off. It will saturate your olfactory glands. Immediately when you smell it, at parts per billion, it just takes your breath away. But if you stick around it long enough, and that's not good, because it actually is not good for you, but the impact wears off. So those are thiols. There's just some examples of naming them. I just want you to identify it. Here's cysteine. This is an amino acid, a really important amino acid, and it's got a thiol on it. And it will form a disulfide bridge, very important in protein structure. We'll look at that in chapter 18.
Professor, where is that tile where it says stage?
Right here. Yeah, one joins to the other. And they split out a hydrogen, two hydrogens, and they form a disulfide bridge. So this isn't the thiol, this is the thiol right here. And there's one on each cysteine. We'll get to that in chapter 18. Okay, at the end of the chapter, I should move this slide. Where was it? Where was that reaction summary? Oh, there it is. Slide 33. This really should kind of be towards the end. But let's look at this, and then I'll go back to those other reaction summaries. I thought this was going to take 20 minutes. Here's your... Okay, this is... Let's just try to get all the reactions of alcohols on here. First, preparation. Preparation of alcohol. You can prepare an alcohol by taking an alkene plus water. That's hydration. That forms an alcohol, right? You can also take an aldehyde or a ketone. In this case, you're going to add hydrogen, hydrogenation, and those will form alcohols. So that would be how are two ways of preparing alcohols? Well, you've learned two ways. You learned that in chapter 11, and we included it again in chapter 12. You learned this in chapter 12. It'll be included in chapter 13. Okay, then there is there's the oxidation of alcohols, and the primary forms an aldehyde, secondary forms a ketone, and the tertiary, there's no reaction. And then we learned the dehydration of an alcohol to form, you can split a water molecule out of the alcohol molecule itself and form an alkene, and you're going to use Zaitsev's rule. to figure out what is the major alkene it'll form. And in dehydration between two alcohol molecules, and you get an ether. Okay, that's a pretty good summary of the reactions from chapter 12. Okay. All right, this one a little longer, so let's take 10 minutes, and during that 10 minutes, take a break if you need one. Finish your chapter 12. Bring your chapter 12 homework up here. I will hand back the chapter 11 homework.
What's the bathroom?